Hey, welcome to Basic Food Theory and Product Knowledge, Lesson 5. Today we're going to be taking a look at heat and how heat gets into the food, moves around in the food, cooks the food. Let's get going. So heat gets into the food in a variety of different ways, and the way that the heat gets into the food affects the outcome, affects the finished product. Um, if it's a dry heat, you're going to caramelize or create the Maillard reaction on the outside of the food, which is going to give you a nice crust, a nice color, etc. And sometimes the heat is more intense, sometimes it's more evenly distributed around the food, and that's definitely going to impact and affect the outcome. So let's take a look at the different ways. The first way that heat transfer takes place is is called conduction. In conducted heat, the heat moves directly from one item to another by touch. So the food is actually touching something that's hot, and that's what makes it cook or allows the heat to move in to cook the food. Conduction also describes the way that heat moves through an item. So as the outside molecules of the food get warm, they heat up the ones closer in and in and in and so forth all the way through the product. A good example of conducted heat transfer is using a griddle. A griddle is a flat top grill. Um, that's the way we call it in the industry, flat top grill, but the actual technique is called griddling. We're going to griddle the food. In griddling, usually it's a cast iron or a thick metal plate, solid plate, gets heated by elements below, either gas or electric elements that heat up the plate, and that gets very hot. And then we place our food onto the griddle so it's touching it, and on the side that's touching the griddle uh, starts to cook. That's a good example of conducted heat transfer. Another example of conducted heat transfer would be sautéing. Sautéing, we'll be describing all the cooking methods in the next lesson, but sautéing is a fast frying technique where you use a sauté pan and that's placed onto an element, electric or induction or gas. The bottom of the pan heats up and we place our food down on top of the hot pan, and that's how the heat gets into the food. It's called conducted heat transfer. Another way that heat gets into food is by putting the food into a closed container surrounded by a hot fluid. And that fluid can be anything from air to water vapor to oil, etc., or water. And this heat transfer is called convection. And in convection, the heat is spread by the movement of air, steam, or liquid around the product. And that could be liquid oil, or it could be water or other liquid stock perhaps. There's natural convection, in which case the hot medium is circulated naturally as a result of heat rising with convection currents causing the heat to rise up and the cooler air to drop down, and then you get this sort of circular motion of heat within a cabinet, within an enclosed environment. Or we can make that process a little bit more efficient by actually moving the air around using a fan, for example, in a convection oven. And this makes this convection much more efficient, evenly distributes the heat throughout the container and so on. The challenge is with natural convection, particularly in some older ovens, the conventional ovens, you get uneven heating around within the cabinet. So if you're baking, for example, you might have to turn the trays around regularly to ensure that things are getting cooked evenly. Whereas within a convection oven with a fan moving the air around, that isn't necessary. So I've given you a couple of examples, but baking or roasting is an example of heating food through convection. And this is done in an appliance called an oven. Now there is fire roasting, and that's different. Fire roasting is a different type of heat transfer. But when you're roasting something in an oven, if you're roasting a piece of meat, if you're roasting vegetables or potato, etc., or if you're baking a cake or cookies, pie, and so on, that takes place in an enclosed unit, an oven, and that's heated up, and you've got your cake going in there, and the convection currents move the air around. As I said, the heat rises and the cooler air drops down, and you end up getting this sort of circular convection motion. And again, you can see in the diagram at the back of the oven, there's a fan. This is a convection oven, so that would blow the air around making it a much more even distribution of heat throughout the cabinet and more efficient. Generally speaking, when you're cooking with a convection oven versus a conventional oven, you can reduce your oven temperature by about 25 degrees Fahrenheit for the equivalent cooking temperature. If your recipe said to cook at 350 degrees, then you could turn your cabinet down to 325 degrees if it's a convection oven. Another example of convection would be boiling or simmering, in which case the liquid is put into a large container, stock pot for example, full of a liquid, water or stock, etc. And in exactly the same process as what we saw with the baking or roasting, instead of the fluid being air, the fluid in this case is a liquid. And again, you get the convection currents moving within the fluid, with the hot molecules rising and the cold ones falling, and you get this sort of circular motion within the cabinet or within the stock pot. And this is what's called convection. And this could be boiling, could be simmering, if you're using poaching perhaps. Or we could make the fluid oil, in which case we'd be deep frying. In this case, we have a closed unit with an element underneath heating up oil, and that oil is heated up to a sufficient temperature to start frying, completely immersed and surrounded by oil. Now this is different from, say, sautéing when there's only a small amount of oil, or even pan frying, in which case there's slightly more oil than sautéing. And I'll describe all of these next week in next week's lesson. But in deep frying, the product is completely immersed in the oil, and you get those convection currents happening within the cabinet as well, within the deep fryer as well. Hot air or hot oil is rising, cooler oil is going down, and so you end up getting this circular motion. Another example of convection heat transfer would be steaming. Again, steaming, the item is in an enclosed unit, either, as you can see here, this Tefal steamer unit. It could be bamboo baskets, but you're enclosing the steam in a product. Remember, water evaporates at 100 degrees Celsius. Once the water is evaporated at 100 degrees Celsius, it leaves the liquid phase, it goes into a gaseous phase, and you get water vapor and steam. And the steam, or particularly the water vapor, is at a temperature higher than the temperature of the boiling water. That's how come the molecules have become airborne. Once they cool down to below 100 degrees, they condense and become water again. But it's the steam that we're going to use as our cooking medium, and so the steam is going to be hotter than the temperature of boiling water. So this makes steaming a very efficient technique, and we'll go into a little bit more detail on this next week. But as we've seen with other convection transfer or heat transfer examples, the steam is contained in a unit, and the product is surrounded by this steam, this gaseous water, and we get the convection currents with the hot steam rising and then the cooler steam going down, and you get the movement of the fluid within the enclosed container. And the last method of heat transfer is radiant heat transfer. And radiant heat transfer means that energy is spread via waves from the source to the food. So unlike conducted heat, the food isn't actually touching the source of heat. Unlike convection heat transfer, this doesn't necessarily have to take place in an enclosed unit. And we're talking about direct radiant energy heating the food. There are a couple of examples of radiant heat transfer. Infrared radiation, where there are elements that are heated to a point where they give off infrared radiation. This cooks the food. And there's microwave radiation, where microwaves penetrate the food and they agitate the water molecules. They get the water molecules to move sort of synchronously with the waves of the energy that's being emitted into the food. And then as the water molecules are moving, they generate friction and they start to heat up. And this is what's cooking the food. Some examples of radiant heat transfer of infrared radiation. A good example would be grilling. Unlike, now you are getting a little bit of conducted heat as the patties are touching the griddles, which are going to be very hot, so that's where you're going to get the grill marks and so on. But the radiant heat is coming up from underneath that, from elements below the food, and that's grilling. Very similar to, as I suggested, that fire roasting would be also an example of radiant heat transfer. So grilling is the radiant heat coming up from below the product. Broiling is we have radiant heat coming from on top of the product, coming down onto the product. And that's the distinction between grilling and broiling. And we'll talk about those next week when we talk about methods of cooking. And another example of radiant heat is, of course, the microwave. And we'll talk in detail about microwaving and so on next week. But essentially, it's microwaves that agitate the water molecules and cause the food to heat up. So what happens when we heat up these nutrients, when we heat up food? This is good to know what happens in food when it gets heated up. First of all, water. With water, when we heat water up, water evaporates. As I suggested when we were talking about steam, once the water gets to be over 100 degrees Celsius, 212 degrees Fahrenheit, it evaporates. And this evaporation is very useful to us. What the evaporation does is it allows us to get volume in food. It causes food to rise. When you think about something like profiteroles or souffle, we kind of capture water inside a dough or pastry, and when the water evaporates, it rises up, swells up, and causes stuff to rise. And that's how we can get these really nice and light profiteroles or cream puffs. We can get this nice souffle as a result of water evaporating. The evaporation also causes a reduction in concentration of flavors. I talked about that in the last lesson with regards to herbs, but it's true of anything. If we're making, for example, a sauce and we want to thicken the sauce, instead of just adding a thickening agent, what we can do is we can evaporate some of the water out, and that'll help to congeal and thicken up and concentrate the flavors. And that's exactly how you would make a product like a glaze, a meat glaze, for example. Just simply reducing down until we've concentrated the flavors, the minerals, etc., into a consistency and a flavor that's appealing. So reduction is a great application of water evaporating. With fats, when you heat up fats, they do a couple of things. They melt. Fats melt, and this is a useful thing for us to know, because this melted fat, first of all, it reduces the fat content of the food. So if you're cooking food, for example, bacon, when you start off with bacon, it's very fatty, but by the time you've rendered the fat out and cooked the fat out of the bacon, and not only does the bacon get crisp, but it's got a much lower fat content. So it might make it better nutritionally, fewer calories, for example. But other things that happen, that the fat gives a sensation of succulence in the food, the melted fat. When you think about eating a piece of bread, for example, it's quite dry, but when you put some butter on it, it gives this impression of moisture. Now, it's not truly moisture, it's what's called succulence. It feels like moisture. Similarly, in some cuts of meat, if you eat, say, a ribeye steak with lots of marbling in it, it's going to have a nicer, more moist mouthfeel. You can cook the steak or the roast to a slightly higher degree because the residual fat in there is going to sort of offset the coagulated proteins, the dryness that come from that, and the evaporated water, and still maintain this sort of moist mouthfeel. So that would be a definite benefit of melting fats. Also, the fats help to shorten starches. You've heard the term shortening, probably. You've probably used shortening in baking. And what it does is it prevents the starches from developing, prevents the gluten from developing into long strands. And it makes baked goods more tender. When you think about cake and cookies and muffins, there's usually quite a lot of fat in those products. And that would help to make sure that you're not eating a tough piece of cake. It's nice and crumbly and nice and moist. So this is a definite benefit of fats melting. Carbohydrates, it does a couple of things depending on the form of the carbohydrates. The sugar, or the mono or disaccharides, the sugars, they do something called caramelizing. And caramelizing adds flavor and color to food. I think we talked about caramelization when we talked about a mirepoix, for example, in the last lesson. Talked about onions caramelizing. You can see an example in this picture of sugar as it's going from clear to caramelized to brown. This will add a nice color to a dish in terms of, say, for example, roasting your mirepoix to get a brown sauce. It also adds a nice richness to the topping. If you take, for example, creme brulee and you just sprinkle sugar on top and serve it with sprinkled sugar on top of a custard, it's not going to be very appealing. If you take a blowtorch and you burn the sugar on top, you caramelize and deeply caramelize the sugar on top, it adds a nice crust to the top of the creme brulee, but it also takes away some of that sweetness and replaces it with more of a richness and even a hint of bitterness, which is nice because that contrasts the sweetness of the custard. Starches, so longer strands of sugars, the polysaccharides, these do something else. When you heat them up, particularly when you heat them up with water, they do something called gelatinizing. And I mentioned this term when we were talking about converted rice last week. But the gelatinization is a really useful thing for us as cooks, because what this does is it helps us to thicken things like soups and sauces and so on. When you think about roux, which is a thickening agent often used in soups and sauces, it's just a fat and a flour. The fat really just helps to disperse and distribute the starch throughout the liquid without clumping together. That's really one of the main reasons the fat is in there. But the starch, it will absorb moisture, and when we add heat, it'll soak in the water and it'll start to swell. And what this does is it swells and it thickens whatever is in there. If you're using a flour in a roux or a slurry, or you're using cornstarch or arrowroot or any of these sorts of starches, the starch granules will gelatinize, absorb water, swell, and thicken up our sauces, our soups, etc. If we overheat these swollen granules, we'll start to reverse that effect. They'll start to degrade and not be as efficient as thickening agents. So try not to overcook any product that's been thickened with a starch. So gelatinization of the starch absorbs water, starts to swell, starts to soften, and it clarifies slightly. Now, some starches clarify more than others. For example, if you're thickening with a flour, it won't really get very clear. But if you're thickening with something like an arrowroot, it will get nice and clear. And proteins. What happens to proteins when we heat them up? Proteins, I mentioned this word a number of times. Proteins do something called coagulate. And what coagulation means is the change of the structure of the protein from a liquid form to a solid or to a thicker liquid. And this is brought about by heat, mechanical action, or acids. Enzymes can also cause proteins to coagulate. For example, when you're making cheese, you use a rennet, which causes the cheese proteins to coagulate. I got this from the Institute of Food Science and Technology. So we can use protein coagulation to a great effect. First of all, when we're looking at cooking meat, for example, if you take a look at the piece of meat on the left, this is cooked to rare. If you look at the protein in the middle, you can see it's still quite gelatinous, still very moist. It hasn't started to tighten up yet. It's still holding on to the moisture, and it's still very tender. So if you have a nice tender piece of meat, like a tenderloin or strip loin, for example, cooked to rare, it's going to stay more moist, it's going to stay more tender. As we, and this rare, we're talking temperatures around 52 to 54 Celsius. As we start to cook it longer, we go to medium rare, and these the temperature for medium rare is 54 to 60 degrees Celsius. Now you can start to see those protein fibers becoming a little bit more pronounced, a little bit more distinct. You can see that it's a little less moist. We're starting to lose some moisture, so you know the meat is getting just a little bit more tough and a little bit more dry. And for certain cuts of meat, that's not so bad. For example, if you've got a ribeye, there's still residual fat that's going to replace that succulence that you're losing from the moisture. But depending on the cut of meat, once you get beyond medium rare, then we're really starting to get dry and tasteless, or dry and tough. This is where you can consider using replacements to replace that moisture, either with a sauce, like a gravy, for example, or with something, replace some fats or add some fats to it using, say, a compound butter melted on top. And that's going to replace that sensation of moisture with the succulence of the melted fat. Once we get up into medium, we're looking at temperature around 60 to 66, and you can see more dry. Those protein fibers are starting to get even more pronounced. And up into the medium well, we can see 66 to 71, and the meat's going to be quite dry, quite chewy, quite tough. And you really, I mean, if this is what the guest wants, you definitely serve it the way the guest would like it to be served. But you certainly have to offset that dryness with a sauce of some kind or compound butter, something to replace that succulence. Otherwise, the meat is not going to be very appealing. And then well done. Well done, we're looking at temperatures anywhere from 71 to 99 degrees Celsius. You can see now very pronounced protein fibers in there, very dry, tough, and again, if this is what the guest wants, this is how you serve it, but you absolutely would need to add a sauce, a gravy, or something to make that more palatable. So coagulation does some things, and I mentioned it to proteins. It causes them to dry out. If you think of a protein or a meat fiber as being kind of a hollow tube, and when the protein heats up, it sort of squeezes, and the inside of that tube, which is mostly water, gets squeezed out, and so you end up with much more dry product. When you think about, say for example, you're doing scrambled eggs, when you cook the eggs bavus, you still have some of the liquid protein that keeps the eggs moist. If you continue cooking, those eggs become very, very dry, and a little bit tougher, not as soft or smooth on the mouth. You can see with meat proteins, they get more tough. Egg proteins, the same sort of thing. Now we can take advantage of the coagulation of eggs. For example, when you're making custards, that's how custards are made. We're controlling the coagulation to a point where the protein is going to be still fluid in the case of, say, a custard sauce like crème anglaise, or a little bit more firm in the case of something like a cheesecake or a quiche. So that definitely is something that we're going to use to our effect. Similarly, when you're making up pâtés, if you don't bake the pâté may be runny still. If you're doing a chicken liver pâté and you're relying on cooking the pâté in order to get that texture, once you puree those chicken livers, they're pretty fluid. So we bake the pâté in a bain-marie to control the temperature, and we coagulate those proteins, and that gives us the finished texture of the pâté. Here's another example showing on meat what happens. So this is chicken. Now this chicken that had been prepared sous vide, so they could control the temperature very precisely. But if you look on the left, we see the chicken is cooked to about to 60 degrees Fahrenheit. You can still see the moisture in there. You can imagine the mouthfeel on that chicken is going to be soft and not tough. And as we heat up that chicken further, you can see right up to 71 degrees, where you can see very pronounced fiber. The chicken is going to be dry. It's overcooked. Now, definitely with chicken, you need to cook it in order to kill off any pathogens. And next week or the week after, when we talk about cooking methods, we'll talk about sous vide. And it is safe to prepare hazardous foods like chicken to less than what the generally accepted temperatures are, but you cook them for a long period of time. It's a time temperature sort of combination that makes the food safe. But even if you cook the chicken in a conventional way, if you cook it to the degree that's recommended by Health Canada, for example, it starts to become very dry and tough. And just like with the steak, if that's the case, and you want to enjoy it, or you want your guests to enjoy it, you have to supplement or replace that moisture with some sort of sauce. And coming up to Thanksgiving, or I guess you'll be looking at this after Thanksgiving, you probably had turkey, may have been overcooked, in which case the gravy, the cranberry sauce really does help to offset the dryness of the bird. Anyway, that's it for this one. Next lesson, we're going to be taking a look at cooking methods. I've already given you a few kind of definitions, but next week we'll take a look at those in a little bit more detail. And we'll talk to you later. Have a good one.